All right, let's do section 7.6, the law of sines, on page 377 of your book. What is the law of sines good for? It is a law that is used to find missing parts of triangles when you do not have right triangles. Okay, and what is the law of sines? It's pretty simple. Given a triangle that looks like this, angles A, B, and C, the opposite being small c from C, the opposite of B side is B, and the opposite side from A is small a. So you can see this triangle. Given that, the law of sines is this: that the sine of A over A is equal to the sine of B over small b, and the sine of C over small c. So you can set up a proportion once you know different parts of your triangle. All right, so let's say we have the following. Let's prove the above sine theory. We're going to prove A and B are equal to each other. Okay? So given the triangle that we had above, I'm making an altitude straight down and making two right triangles out of that triangle, putting in point D. I've labeled that altitude as H, or the height of the triangle. So what do we got? As soon as we do that, we now have two right triangles, ADC and BDC. So we've got two halves of this triangle are now right triangles. Well, when we have a right triangle, we know that the sine of A for this small right triangle is equal to its opposite, which is H, the height of the whole thing, over its hypotenuse, and that's the right triangle, so the hypotenuse is B. Sine of A is equal to H over B. Well, the sine of B from the other side, the other right triangle, is also its opposite, H, happens to be the same dotted line in both of these cases, over A, which is its adjacent. So now I'm just going to set those two equal to, or I'm going to cross multiply each of those, H times the sine of A, okay, or H times 1, sorry, this is really a 1 and a 1, so H times 1 is H when I cross multiply, and the sine of A times B. And over here I did the same thing. Sine H times 1 is H, sine of B times A is sine of B times A. Okay, now I'm just going to substitute. Since H, they're both equal to H, I'm just going to set each side equal to each other. So the sine of A times B is equal to the sine of B times A. Well, I'm going to divide both sides by A, and that gives me this oddball guy here. And let's not look at that yet. And let's not look at, sorry, got to grab another piece of paper. Let's not look at that yet. Okay, so when I divided this by A, I get the sine of B is all that's left on this side, and I get the sine of A times B over A on this side. Well, now I want to get rid of that. I want to put the B onto this side. I do that by multiplying both sides of the equation as 1 over B. So there's that multiplication. And there's 1 over B on this side. And when I finally do that multiplication, I end up with the sine of A over A is equal to the sine of B over B. And that is the proof. You can then follow up with this same logic to figure out the sine of B is equal to C, and the sine of B over B is equal to the sine of C over C, or the sine of A over A is equal to the sine of C over C. So you can do all the calculations, but it's just a repetition of this. Okay, so that's the proof. Now let's look at some examples. Example 1A in your book basically says this: given this triangle right here, ABC with the following degrees, and B is what we're looking for, and 3 is the side opposite of the angle A. We're just trying to find B. Well, first thing we notice is that we can set up the law of sines here. This is not a right triangle, so we're going to set up the law of sines. The sine of A over A is equal to the sine of B over B. We're looking for B, so when I substitute that in, I end up with a pretty easy substitution. Sine of 37 degrees over 3 is equal to the sine of 68 degrees over B. And I then divide both sides. I'm trying to get, or then I cross multiply. I'm trying to get B by itself, so I cross multiply and I get 3 times the sine of 68 on this side, and multiplying this way I get B times the sine of 37. I then divide both by the sine of 37, and I finally end up punching that into the calculator. B is equal to approximately 4.6. How about this problem? What if I'm given this set of problems? I've got x, y, z. The side opposite of y, small y, is 17. The side opposite of z, small z, is 14. Okay, y is 92. They're saying find the angle for z. Well, once again, I'm going to use the law of sines. I can find different parts of a triangle using the law of sines. So I'm going to start with the sine of y over small y is equal to the sine of z, which is what I'm looking for, is z, capital Z, over small z. And when I substitute that in, I get the following. Sine of 92, which is my y, over 17, which is my small y, is equal to the sine of capital Z, which is what we're looking for, over small z, which is 14. Opposite is 14. I then do the quick calculation, cross calculation, or cross multiplication. I get 17 times z, sine of z on this side, and on this side I get 14 times the sine of 92. I divide both by 17 to get sine of z by itself, and that's what I get. Sine of z equals 14 times the sine of 92 divided by 17. But now I have to do the opposite function, or the inverse function of sine, to move sine away and leave z by itself. And to do that, I do the sine -1, or inverse sine, or arc sine of the same calculation I just had, 14 sine of 92 divided by 17. I punch that in my calculator, and I got z is approximately equal to 55 degrees. And thus, the measure of angle z is approximately 55 degrees. That's 1A and 1B. Let's look at example 2 now. Example 2, it says solve the triangle. What does it mean by solving the triangle? That means to find the measures of all the sides and angles of a triangle, of a given triangle. And they'll give you some of them so that you have enough information to solve it. So here's our problem. We need to solve the triangle ABC here. Okay? And here's what we're given. We're given that this angle, angle A, is 33, angle B is 47. We're not given C or A, which are the side lengths, but we are given that side B is 14. So what does that leave us to solve? We need to solve the measure of angle C, and then how long this side is A, and how long this side is C. So first of all, the first thing I know I have is a triangle. I'm going to find the measure of angle C very simply by saying the measure of angle C is equal to 180 degrees minus the other two measures that I know. And the other two measures that I know are 33 and 47. So 180 minus 33 minus 47 tells me that the measure of angle C is 100 degrees. So I know that that guy is 100 degrees. All right, now let's move on. We've got to find A and C yet. Okay, so we're going to find them simultaneously because it's the same problem, step by step by step. As we go down through this, I'll just uncover each step of both problems at the same time. We're going to use the law of sines. On this side, to find A, we're going to say sine B, the sine of capital B over small b, which is known quantities, is equal to the sine of A over small a. And the same thing is going to happen over here. The sine of capital B over small b is equal to the sine of C, capital C, over small c. And when we plug in what's known, you'll notice that the sine of B over B is the same on both sides. Okay? So then all we have to do is get the sine of A, which is 33 degrees, over A, which is what we're going to solve for. And on this problem, the sine of C is 100. Remember, we just solved for that right here, so that angle right there is 100. So sine of 100 over C, which is what we're solving for on this side. Now we come down and do our cross multiplication, and when we're done doing a cross multiplication, we get 14 times the sine of 33, multiplying this way. Multiplying this way, we get A times the sine of 47. Once again, we multiply this way, we get 14 times the sine of 100, and this way we get C times the sine of 47. Now we're going to divide by the sine of 47 on this side to get C by itself, and on this side the same thing to get A by itself. So we end up with the following equations. A is equal to 14 times the sine of 33 all over the sine of 47, and C is equal to 14 times the sine of 100 all over the sine of 47. And when you punch that into your calculator, you get the following numbers. And so A is approximately 10.4 and C is approximately 18.9. And thus we have solved for this triangle that we started out with. We found the missing angle, C, and the two missing sides, A and C. And we've solved that triangle. And finally, let's use a real-world problem. Let's say we have the following problem, and you got to kind of follow this close. There's a picture in the book is a little better than my drawing. All right, here's the picture. We have an imaginary right triangle of perfectly up to the sun. Point S, the sun, B is where the ground meets this. The pole in the goes into the ground, and this line here represents a pole that's in the ground. And G is the shadow, the point at which this pole drops a 30-foot shadow. We know that from the end of the shadow directly up to the sun through the top of the pole is 62-degree angle of elevation. Okay? We know that the shadow is 30 feet, and we know that the pole is leaning in the ground at 7 degrees. We are to find the length of the pole, and that is line PD here. Okay? Well, the first thing we know is that angle GDP, this angle, which is the pole coming out of the ground, we want to know what that angle at the bottom is. Well, we know that we have a right triangle, the one that goes up to the sun, and we know we're missing 7 degrees. So 90 minus 7 is 83. So we now know that this angle here is 83 degrees. What else do we know? We know that angle GPD, this top angle up by the sun, okay? Sorry, not by the sun, GPD, the top of the pole, this angle right here, is going to be 180 degrees, because that's what a triangle has, minus the 83 that we just figured out, minus the 62 that was given to us. And we know that that is 35. So now we know that's 35 and that's 83. So now I can use the law of sines. And I'm going to use the law of sines like this. Let's not look at that yet. The sine of P, so there's angle P over its opposite, P, is equal to the sine of G, 62, over its opposite, which is G, typically small g. But I'm going to replace small g with PD, which is the line segment that represents how tall the pole is. So when I substitute all that in, I get the sine of 35, which is our angle up here, P, all over P, which is 30, is equal to the sine of 62, G, and over PD, which is the length of our poles, what we're looking for. We then cross multiply 30 times the sine of 62 on this side, and going this way, PD times the sine of 35. Well, we want to solve for PD, so we're going to divide by the sine of 35 in both places, and divide on both sides. And when we get that, there's our formula. PD is equal to 30 times the sine of 62 all over the sine of 35. And when we calculate that out, we find out that PD, or the length of the pole, is approximately 46.2 feet.